So, I want you to imagine a scenario for a second. You're sitting at a desk, and you are an underwriter.
Right.
But, you're not insuring a car or a house or, like, a commercial shipping fleet. You are insuring a massive, highly complex software code commit.
Which is incredibly stressful, honestly.
Oh, absolutely. I mean, the stakes are just astronomical here. Millions of dollars, maybe even the entire operational stability of some massive financial institution are riding on this specific block of code executing perfectly.
Yeah, if it fails, it's catastrophic.
Right. If there's even a tiny logic error buried deep in the syntax, systems crash, money just evaporates, and the liability falls entirely on your shoulders.
Yeah.
So naturally, you have an automated tool, right? Something that checks the code for you before you actually sign off.
Yeah.
But here's the problem that probably keeps you up at night. How do you know for an absolute fact that the tool checking the code isn't just hallucinating?
And that's really the million-dollar question for anyone managing risk in modern systems right now.
Because we rely heavily on these tools.
Exactly. We rely on automated checkers because code bases today are just far too large for human eyes to parse in real time. But the checkers themselves are just software. They're fallible.
Right.
They can misinterpret data, or, even worse, they can confidently output a passing grade based on entirely corrupted logic.
So what if, and this is the core of what we're looking at today, what if, instead of just hoping that your automated tool was having a good day, the tool could cryptographically prove to you that it was awake, sober, and completely calibrated to your specific environment mere milliseconds before it signed off on the code?
I mean, it sounds like science fiction.
It really does.
But that's exactly the paradigm shift we are looking at today. We are moving from a world of assumed trust to, mathematically proven certainty. And it just changes the entire landscape of risk in software engineering.
It really does. Welcome to today's deep dive. We're unpacking a genuinely fascinating technical document today, and it's titled the Zero Trust Actuarial Instrument, On-Chip Calibration and Attestation.
It's a dense one, but so worth it.
Very dense. But our mission over the next few minutes is to basically figure out exactly how software can use a dynamic, stacked battery of self-tests to prove its own reliability instantly.
Right.
We're talking about taking a theoretical math model and transforming it into an insurable, zero-trust actuarial asset.
Yeah.
And the detail that completely threw me when I first read this, it accomplishes all of this without making a single call to a large language model.
Which is wild because in an era where the default solution for, basically any complex analysis is routing data through some massive AI in the cloud, this approach goes in the completely opposite direction.
Yeah, it goes local.
It goes microscopic, actually. It goes all the way down to the physical silicon.
So to understand just how groundbreaking the Zero Trust instrument actually is, we really have to start with the core insight of the document. The authors describe this necessary shift from what they call a generic ruler to a tuned seismograph.
Right. So previously, the industry standard relied on what they term a static-derived ceiling.
Okay, break that down for me.
Sure. So you have a mathematical model that has been proven to work on paper in a lab setting. You run your company's code base through it, and the math says the code falls within acceptable parameters of risk.
Got it.
It's a generic ruler. A foot is a foot, a meter is a meter, and it just measures whatever you put in front of it using that exact same fixed standard.
Right, but a static ruler doesn't know anything about the environment it's in. Like if I'm using a ruler to measure a piece of wood on a table, the ruler doesn't know if the table is shaking or, if the wood is rotting from the inside.
Exactly.
What this new instrument does feels fundamentally different. The text says it uses a dynamic, stacked battery of perturbation tests to prove the physics actually work on this specific code base right in this exact moment.
Yeah, the active nature of the measurement is the real breakthrough here. It's not just measuring the code, it's aggressively measuring its own ability to measure the code.
Wow.
It's proving that its internal logic actually holds up under the unique pressures of whatever specific software environment it happens to be looking at.
And that leads to the analogy I really love from the text. They say it proves the instrument isn't a generic ruler, but a seismograph tuned to your exact fault lines.
Such a great image.
It really is. A seismograph is actively listening to the ground beneath it, calibrated to the specific vibrations of the earth it's actually anchored to. But I found myself pushing back on the premise here when I was reading.
How so?
Well, we live in 2026, right? If we have this incredibly complex problem of verifying code semantics and making sure a system isn't hallucinating, why aren't we just throwing a massive large language model at it?
Right.
Like, why not just ask an AI, hey, check this code, make sure it's legally and financially sound, and, promise me you aren't hallucinating.
It's a totally natural assumption, especially given how dominant LLMs are in our daily workflows now. But the source text outlines exactly why that is dead end for this specific actuarial application. The barrier is physical. It comes down to speed, cost, and determinism. LLMs require massive compute. You're taking the data, packaging it up, sending it over a network to a cloud server where, billions of parameters are calculated, and then waiting for an answer to come back.
So we're talking about a delay of what, a few seconds? In human conversation, that's nothing.
True, but when you are that underwriter trying to facilitate high-frequency automated transactions, a few seconds per commit is a catastrophic bottleneck.
Ah, right. It just doesn't scale.
Exactly. Furthermore, LLMs are fundamentally non-deterministic.
Meaning you get different answers.
Right. You can ask an LLM the exact same question twice and get slightly different answers based on the temperature of the model. You just cannot build a zero-trust actuarial asset and insurance policy on a system that might subtly hallucinate a connection that isn't there just because of a probabilistic coin flip.
Yeah, that makes total sense. If you are legally guaranteeing million-dollar code, you need something that gives you the exact same answer 10,000 times out of 10,000.
Precise.
So if we aren't sending this to a cloud AI, how does this seismograph physically operate?
The system uses a mechanism they call the Definer Walk 144. And the critical architectural detail here is that this executes directly on chip.
But I want to make sure I'm visualizing this correctly. When they say on chip, they mean the verification is happening right there on the local hardware at the processor level without ever asking the internet for help.
Yes. Think of the difference between the cloud and on-chip execution, like the difference between sending a letter to a committee for review versus triggering a physical reflex.
Oh, interesting.
The LLM is the committee. It's smart, but it's distant and it's slow. The Definer Walk 144 is like a microscopic tripwire built directly into the floorboards of the server. Because it's a localized physical process executing at the silicon level, it runs in under a millisecond.
Under a millisecond, less than 1,000th of a second.
Yeah.
So the speed completely changes the strategy. Because it operates that fast, it has the luxury of constantly testing itself without slowing down the actual work. The text mentions it runs a battery of 20 walks, which are essentially 20 complex self-interrogations to mathematically prove its own health.
Exactly.
And because it's so incredibly fast, the compute cost is practically zero.
Right. It becomes this self-contained, lightning-fast loop of verification. The instrument actually has the processing overhead to try and break its own logic repeatedly before it ever even looks at your code.
Okay, so the instrument is lightning fast. But what is it actually doing during those 20 walks?
Right.
The document details a very specific three-step asynchronous process to validate the system's health, which they call the stacked battery.
Yeah. The stacked battery has to independently prove three distinct things to the underwriter.
Okay.
First, it has to prove it's not hallucinating. Second, it has to prove it actually understands the meaning of what it's reading. And third, it has to prove it is properly calibrated to the right contextual environment.
Let's unpack the mechanics of that, starting with experiment 1, which they call signal decay, or testing for monotonicity. The document uses this phrase, perfect intent as reality grid. I'll admit that tricked me up a bit. What are we actually looking at here?
Yeah, intent as reality grid is just their highly specific jargon for the code commit itself.
Oh, okay.
It's the literal payload of code where the developer's intent is supposed to match the reality of the syntax. The instrument takes that payload and it deliberately starts deleting it. First, it deletes 50% of the payload. Then it deletes 100% of it.
Wait, it's essentially covering its own eyes. Why would an inspection tool actively blind itself?
It wants to observe the corresponding reaction in its own internal confidence score. The text refers to this internal signal strength with the symbol sigma.
Okay, sigma.
You can think of sigma as a literal measurement of how tightly the algorithm is gripping the logic of the code. If the data is suddenly cut in half, the instrument's grip should correspondingly weaken.
That makes sense.
The mathematical proof here is that the sigma must decay monotonically.
Monotonically meaning it has to go down in a straight, predictable, proportional line that exactly matches the deletion.
Yes, exactly.
I was trying to come up with a way to visualize this for myself. It feels a bit like being at a concert and turning the master volume down on the mixing board. You drop the volume to 50% and then you pull the plug entirely to 0%.
Okay, yeah.
If someone on the dance floor is still dancing wildly when the room is dead silent, They aren't actually listening to the music, they're hallucinating it.
That captures the underlying physics perfectly. If the data payload drops, but the instrument sigma stays high, meaning it still claims to be getting a strong read on the logic when the code is literally gone, then the sensor is hallucinating.
Right.
It's reacting to residual noise, not actual input.
Do the numbers in the document actually bear this out? Like, what happens to the sigma when they pull the plug?
They do. The text gives us the exact telemetry. At 100% payload, the sigma registers at a healthy 28.8. When they delete 50% of the data, the sigma drops to 14.1, which is roughly half.
Okay.
And when they delete 100% of the data, the sigma collapses all the way down to 0.1.
Wow. So the decay is perfectly monotonic. It tracks the disappearance of the data flawlessly.
Exactly.
It proved to itself mathematically that it requires actual input to generate a signal, which passes the hallucination test. But, understanding that the music has stopped is only step one. How do we know this instrument actually understands the meaning of the code?
Right.
How do we know it isn't just recognizing the structural shape or the layout of the text, like a scanner reading a barcode?
And that vulnerability is exactly what Experiment 2 is designed to expose. They call it Semantic Substitution, or the domain fit test. This is where the instrument goes beyond deleting data and actively tries to sabotage its own comprehension.
Oh, wow.
It utilizes what they call a replace-all crosswire.
What does a crosswire look like in practice on the chip?
So the script identifies the dominant thematic axis in the current commit. Let's say the code being submitted is heavily focused on legal parameters and compliance. The text uses the axis strategy.law.
Okay.
The instrument then executes a force replacement. It takes the defining keywords of that legal axis and replaces them with an orthogonal axis, meaning a completely unrelated vocabulary.
Oh, I see.
For example, it swaps out strategy.law with strategy fund, suddenly injecting financial terms into legal architecture.
It takes a dense legal document and suddenly forces financial banking vocabulary right into the middle of the sentences.
Exactly.
It would be like reading a recipe for a chocolate cake, but halfway through, the instrument replaces the words for flour and sugar with the words for spark plugs and motor oil.
That's a great way to think about it.
Right, because if I'm actually reading for comprehension, I immediately stop and say, wait, I can't bake a spark plug. This makes no logical sense. But if I'm just scanning the structure, like just looking for a list of bullet points followed by a numbered list of instructions, I might just keep reading right past the error.
And that is the core mechanism of the test. If the instrument is genuinely reading semantics at the silicon level, if it understands the meaning of what it is processing, then the walk must derail.
Right.
It has been forced into orthogonal lanes that make no logical sense together, and therefore the sigma, that internal grip strength, must collapse.
It has to fail.
Exactly. If the sigma survives the substitution, it means that the system, which they refer to as the reef, is just reading structural noise. It's reading the formatting of the recipe, not the ingredients.
Does the document say how bad the failure is when it's forced to read nonsense?
It does. They detail a specific test where they did a vocabulary inversion, shifting the axis from C2 to B1. The result was immediate. The sigma collapsed from 28.8 all the way down to a negative 1.2.
A negative score.
Yeah.
So it didn't just lose its grip, it aggressively registered that the logic was corrupted. It tripped over the trap it set for itself.
Perfectly said.
Okay, so we've established it isn't hallucinating, and it actually comprehends the semantics of the code. That brings us to experiment 3. Repo Center of Mass, which they call the tuning test. It understands the words, but how does it know it's applying the right rules for the specific company it's working for?
Right, because software repositories are living environments.
Yeah.
The terminology a financial firm uses in their code base might mean something entirely different at a healthcare startup. The instrument needs to prove that it is actually calibrated to the specific current environment of the code base it's evaluating.
How does it do that?
To do this, it checks the geometry of the current commit against the 30-day moving average of the repository.
Why a 30-day window?
It acts as a recent historical baseline. It's checking to see if the work happening right now aligns with the coordinates the reef has mapped out over the last month. The text notes that in their successful test, the reef covered 92% of the trailing 30-day commit volume. It proves the instrument is deeply embedded and accurately mapped to the specific history of the team's actual work, rather than just floating in some theoretical void.
So if a developer suddenly started writing code in coordinates the reef hadn't mapped over the last month, The instrument would realize it was out of its depth and just flag itself as uncalibrated.
Exactly. It has built a flawless chain of self-verification. It checks its eyes, it checks its comprehension, and it checks its map.
Which is incredible from a purely computer science perspective. But I want to bring this back to the human element for a second.
Sure.
If you're that underwriter we talked about at the beginning, sweating over this massive code commit, you aren't running these on-chip perturbation tests manually.
No, definitely not.
You just need to know if you can sign off on the liability. So how is all of this complex sub-millisecond math actually presented to the human whose job is on the line?
The user experience is surprisingly straightforward, actually. The document outlines how the outputs are tiered. The deeply granular methodology like the raw data from the 3 experiments we just discussed is appended to an HTML attachment. They call this the triptych.
So the heavy math is preserved for auditing purposes, if a risk analyst ever wants to really dig into the physics.
Exactly. But for the immediate workflow, the raw attestation numbers surface directly in a clean email.
Oh, just an email.
Yeah, the email body remains entirely focused on the transaction itself, carrying the instrument attestation right at the bottom.
Okay. I want to look at a scenario where things don't go perfectly, because that is where an underwriter's career is usually saved or destroyed.
Right.
What happens when the instrument actually catches an error or realizes it has become uncalibrated? The text provides a specific example of an email payload where the verdict is undetermined. Walk me through the forensic data it provides there.
The payload breaks down the failure really methodically. So the verdict is undetermined. Underneath that, it lists the nature of the failure. Lens calibration required, noting a bottom-up horizontal line.
Okay.
Then it provides the vector, which pinpoints the exact moment the logic crossed a wire it shouldn't have. Ops, Loop Redefining Strategy Fund, C2 to A3.
Oh, so it caught the semantic collision.
Yes.
And then it provides the rationale, which feels like the most critical part for an underwriter trying to understand what actually went wrong.
Yeah, the rationale notes a suspect read. The sigma dropped to -0.46. The instrument explicitly states this is not evidence.
Wow.
And then it provides this really striking visual for the telemetry. 12 out of 12 tiles gripped nothing under a systemic line.
12 out of 12 tiles gripped nothing. That is such a visceral way to describe an algorithm failing to find a solid foothold in the logic.
It really is.
It reached out to analyze the code, and its hands just slipped right off. Because of that total loss of grip, it diagnoses the problem as lens blindness rather than drift. Why does the text make such a point of distinguishing between blindness and drift?
Because drift implies that a model is slowly becoming less accurate over time.
Yeah.
It suggests the generic ruler is just getting slightly warped.
Right.
Lens blindness is entirely different. It means the instrument realizes it literally cannot see the current structure clearly enough to make a safe judgment. It's a localized failure of the instrument's calibration, not a fundamental flaw in the overall model itself. Because it knows it's blind to this specific commit, it doesn't just guess.
It doesn't flip a coin.
Exactly. The verdict abstains, and the implicated lane is simply routed to reef calibration.
It's the ultimate failsafe. It basically says, I can't ensure this right now. I don't have a strong enough grip on the logic. Send me to the shop for a tune-up. That is incredibly reassuring for an underwriter. Now let's look at the flip side. When the code is perfectly sound and the instrument is completely healthy, what does the final seal of approval actually look like?
The text provides a precise timestamp for a live hardware validation. They give 2026 Euro 6 15T 23.20.30Z. At that exact second, all 3 experiments register a pass.
Right.
When those passes align, the system generates a bearer policy sealed. The core of the seal is a cryptographic string, specifically an ED2551 signature.
We hear the term cryptographic signature a lot these days.
Yeah.
But in this specific actuarial context, what is that ED2551 signature actually doing? Is it just like a complex password?
It's far more robust than a password. It is a structural bind. That signature permanently anchors 3 disparate elements together.
Okay.
First, the input, which is the code commit itself. Second, the live instrument health, which is the exact telemetry of those stacked battery tests. And third, the final verdict.
It's like a digital knot. It proves not only that the code was approved, but that the inspector was of sound mind and perfectly calibrated at the exact millisecond the stamp came down.
Exactly. And the power of that cryptographic knot is its fragility.
Its fragility.
Yeah. If a developer tries to alter even one character of the code after the fact, or if someone discovers the instrument's health had actually been compromised, that ED25519 signature would immediately shatter.
Wow.
It mathematically proves the exact state of reality at the moment of underwriting.
So bringing this all together for our underwriter, staring at that massive, terrifying code commit, how does this zero-trust instrument fundamentally change their job?
It moves them from a position of faith to a position of cryptographic certainty. You are no longer just trusting that a software engineer wrote clever math a year ago. You aren't relying on a generic ruler that might be ignoring a shaking table. You are looking at mathematical proof that the instrument actively tried to break itself, actively tried to hallucinate, and actively tried to misread the semantics mere milliseconds before minting the token, and the physics held up.
You don't have to believe the software works. The software proves it works on the physical hardware level every single time it makes a decision.
Precisely.
Let's take a breath and just recap the journey we went on today. We started by looking at the old world relying on static code-based rulers that just check the math on paper.
Yep.
We explored the necessary leap to a dynamic, self-sabotaging seismograph. We broke down how the system uses the definer walk 144 to execute sub-millisecond on-chip physical reflexes, completely bypassing the massive compute costs and non-deterministic nature of cloud-based LLMs.
Which is a huge leap.
Massive.
Yeah.
We walked through the stack battery, how it checks for hallucinations through signal decay, how it proves semantic comprehension by surviving crosswire substitution, and how it verifies its local map through Repo Center of Mass.
Right.
And finally, we saw how all of that invisible physics is bound together in an ED25519 cryptographic seal, delivering a zero-trust insurance policy right to an underwriter's inbox.
It is a microscopic, highly elegant solution to a massive macroscopic problem of risk management. It really redefines what it means to validate automated work.
It really does. And it leaves me with a thought that I want to pass on to you as we wrap up today. We've just explored a world where complex algorithms can use hardware-level physics to cryptographically prove their own sanity.
Yeah.
They can prove their semantic understanding in milliseconds, entirely bypassing AI. So what does that mean for the future of human trust?
That's the big question.
It is. When every automated decision system in our lives, from the software approving our mortgages to the logic navigating our autonomous vehicles, can instantly prove it actively tried to break its own logic and survived, will trusting your gut become entirely obsolete?
Right.
When the machine can definitively prove its own sanity, what is the residual value of human intuition?
That is a profound question to consider as these systems become more and more integrated into our daily lives.
Thank you for joining us on this deep dive. Next time you're relying on a system to keep you safe, just ask yourself, is it a generic ruler or is it a seismograph tuned to your exact fault lines?